Okay, let's begin. We're going to come back around to going through this implementation on Gibbs. We'll spend quite a few minutes going through it. I'll show you aspects of this code. This code is also online for you to play around with. And so if you want to use this as a template for your future homework, you can, but this is all stuff that you can write by yourself too. And you probably should write the whole algorithm just by yourself. So this is about as easy an example in MCMC as you can get. It's slightly elevated because you can't, well, you could use a symmetric proposal. We're talking about it for the variance term, but you might not want to. So there's a few little aspects to it, and it's a two-dimensional analysis. And I ask you to do this two different ways, where I'm asking you, you can either update everything in a block, or you can do it sequentially. And I'll try to explain what that means real quickly. So anyway, we'll come back around to the MCMC implementation and go over various details, why you would do something versus doing something else. At the beginning of all of this, it's never quite clear where you're going with things. And so I'm going to show you certain aspects of stuff that you don't really need to know yet, but in a couple weeks' time, becoming MCMC experts, you would want to know all these details. So we'll go through that in a couple minutes. I posted a new homework for you. I made it due not this Friday, but the Friday afterwards. We might need another weekend in there, and so I'm open to extending if we need to, because there's still several things I haven't told you in this homework. But if you want to read through it and get ahead, there's definitely problems that you can solve right now. So problem 1, part 1, I want you to sample from a Cauchy distribution that's centered at 0 with scale parameter 1. The covariance structure that I want you to include is this thing right here. It's not the covariance estimate, because it's not variability. So that's a bad descriptor, but it's really your scale matrix that you're going to be playing around with. And so I shouldn't have used the word covariance, but I did anyway. And so in some aspects, you can think about it as covariance if you think about mixture representations of Cauchys. So I just want to point out how you do this sampling from a t-distribution. A Cauchy is a t1. I can show you one way to do it. So one way to do it is you go to your multivariate t package and you generate from it. It used to be that Cran didn't have that. So you'd have to build this up yourself. Nowadays, all those things are there. Another way to generate from a Cauchy distribution is to use that gamma scale mixture representation of everything. And so what you might do is you might generate everything from a normal distribution. So I might generate x and y. These are just bivariate point from a normal distribution that's centered at 0. And I build in my covariance matrix. So this thing is that matrix right there. So that's a 1, that's a 1, 0.8, 0.8. So you could generate this. This isn't t yet, but I could make it a t real quickly by doing one step. I could say sample the gamma, and I'm going to put an I right there, where that's an I, and that's an I. And my gamma parameter comes from this distribution, nu over 2, nu over 2. So you can work this out if you wanted to, but if you wanted to sample from a t-distribution, this is a t-distribution in disguise, for the same reasons that you figured out on your previous homework. So in general, this parameter upstairs is the degree of freedom. So for a Cauchy distribution, this thing would be 1, because a Cauchy is a t1. So I want to just point out what's happening right here. If gamma gets small, so if gamma is small, and sometimes it's small, it's always positive, so we're in good shape right there, this thing gets big right here, and that's the heavy-tailed aspect of everything. That's what's pushing things off into the tails. You can kind of see that probably those should be the same parameters right here, that the expectation of this gamma, and the representation I'm using has the expectation alpha over beta, not alpha times beta. And so the expectation of this is 1, so on average, this is kind of like a normal distribution, but the tails are very different. Maybe you think about your t's like that. So you could do it like this. If you could sample from this normal distribution, then you could also sample from a gamma and turn those realizations into t-realizations. Or you can use the CRAN package or whatever package you have. But if you ever get stuck on sampling something, some of these representations can be really useful. So these will give you perfect t with new degrees of freedom samples. So we don't have to wait for them. So like an MCMC. Just real quickly, how do you sample from that? Let's say you can only sample from a normal 0, 1. So say you only know how to sample normal 0, 1s and these gammas. Now this is maybe a little bit of a fiction, but sometimes those are the tools that we have in our hand. So if I only knew how to sample from a normal 0, 1, how would I sample from this top layer? I want 5 variant samples that are correlated. I can create independent samples. So we already know if we did something like this, I could take my normal 0, 1s. Let's say I had an x that was normal 0, 1. If I wanted to turn this into a shifted normal, so if I wanted to change that to maybe mu, all I have to do is take x plus mu, right? And that's just going to slide it right over. So I can do it in one step. But if I change this to sigma squared, the variance, what would I need to do to this? To turn it into a normal with variance sigma squared in mean 0, or mean mu. This is super simple. Yeah, I take sigma and I multiply it by x, right? So that's what you do there. So you rescale the problem. These are location scale families, and you can play around like that. Slightly harder question. How do I take samples from a normal 0, 1? So let's say I got an x and a y. X is sampled from a normal 0, 1. This is sampled from a normal 0, 1. Now I want to correlate them with that thing. What do you do? We know how to shift it. If I wanted these to be shifted in mu, I just take both of them and I add mu to it, whatever the mu vector is. So if I had a mu1, mu2 that I wanted to shift, I'd just add mu1 to that and I'd add mu2 to that and shift everything appropriately. I'm talking about rescaling it now. How do you do it?
You can use the traditional expectation formulas, maybe?
Maybe. So we're not going to change it from a margin to look at its conditions. So if I wanted to come up with the distribution of x given y, I might do that.
Maybe find the joint distribution and then multiply the inverted correlation variance matrix.
Inverted correlation matrix, something like that. So I did generate bivariate pairs right here. They're just independent. So I've already got those. So Perul's onto something. That won't work. That's not quite the right form. But remember, if I took x times sigma plus mu, and this was normal 0, 1, then this whole thing is normal mu sigma squared. So that's getting squared out right there. You know what variance is. You can see where that square came from. So what do I do here? Here's the thing. You write down this, A times A transpose, if you'd like. So A is something like sigma to the 1/2. So those are like the same things in some sense. These are not unique. There's an infinite number of ways you can do this factorization. Does anybody know what that factorization is called? They don't teach you this stuff anymore. It's the Cholesky. There are different forms. You could come up with some LU representation, and there's in infinite ways you can form Cholesky factors, but only positive definite matrices have this factorization. So just like I can't take a negative number and take the square root of it. So I can't take any number and go from sigma squared over here. I mean, you can, but we're going to get into complex analysis. So it's different. So same sort of analog that if this is a positive definite matrix, real quickly, what's a positive definite matrix? You know what it is to me? It's that I can write it that way. So if I were ever going to check a matrix to see if I could, if it were positive definite, I would do Chol sigma. And if it came back and it barked at me, it would be running the algorithm and see that you would divide by something you can't divide by. If you know how the algorithm works, and it would say you failed. Can't run the algorithm. And it's the fastest way on the planet to check positive definiteness. You could also get all the eigenvalues and make sure all the eigenvalues were positive. So that's positive definite. Semi-definite has the 0 in there. Turns out a Cholesky algorithm can be modified to do the semi-definite thing. But if it's negative definite, then no go. So, or if it's not even that, no go. So Cholesky factorization. So I like to just check this. So Chol, you could come up with other formulations. You could do the spectral decomposition if you wanted to. So you could do something like this. Here's another definition. Is I could take my eigenvalues and I could end up pre and post multiplying by my eigenvectors. Right, like that. What they taught you in high school. I'm not sure when we learned this. In college at some point, your first linear algebra class. So if you can write sigma like this, you can come over and take the half power of those. That's really easy to do. It's a diagonal matrix, the eigenvalues. That's the slowest way you could possibly do this problem. It'll also work. So you could take this thing right here, or you could take the whole thing right there, the half power, and multiply into your draws right here. So what you're going to do with this is you're going to take your Cholesky factor, however you think about it. So sigma half times xy. And if you wanted to add mu1, mu2 in there, so that we wanted these to be shifted at mu, you could do that. This problem's not asking you to change the center, so you don't need this. But you could take bivariate normals and rescale them through the Cholesky factor, and you would come up with stuff that's correlated. That's a beautiful thing. You can't do that with Cauchy's. So I've seen this done many times on the homework. So people do this. This is wrong. I've seen people go through and they collect their samples out of Cauchy 01s. So they might take X and Y. These both come from Cauchy 01s. And then they take sigma half power, that Cholesky factor. So they just type Chol, plug in that matrix, it gives you another matrix. If you want to make sure it's the Cholesky factor, transpose it and multiply it into itself, and you'll get that same matrix back. So you can't do this. So these are not bivariate Cauchys. Can anybody see why? So let's just think about what does a bivariate Cauchy even look like in the first place. So let's say I had maybe normals with centered at 0. with covariance terms 0.8. They probably look like that. The slope of that thing is like 0.8. That's what it means to us. So normals look like that. Bivariate Cauchys kind of look like that in the bowl. It's just like a Cauchy distribution, but every once in a while you have these points. So way out there, over there too, you know. So all over the place. If you've ever, you know, wanted to entertain yourself, just generate Cauchys and look at it. You know, it's pretty cool. So they'll look crazy right here. If you do this right here, you're going to make a mistake, and I've seen people do this, that the X might shock. So it does that big jump. So that big jump, the deviation, we'll call a shock in the system. I like that one. It's not a technical term for this. So this might shock in that direction, but the chances are that that shocks together with it at the same time that it's way off in the tail is small. So probably not. So this would jump and that wouldn't jump together. And what that would do, if I ended up generating the normals, or the Cauchys, right here I have something that goes like in this direction, and then bang, bang, and then I'd have stuff in this direction, and every once in a while that would go bang, bang, something way up there. Then when I did this, I'm rotating it. This is a rotation matrix. So if you like to think about it that way, we're just rotating the space. And so this thing would, there'd be a lot of stuff here in the middle. There's probably too many of these points out here. But there'd be a couple of them out there. And then when I rotated it, you would see this crooked cross. And so if you see the cross, you've made a mistake. And I know what you did. You generated these first, and then you rotated the thing. So that won't work. So you can't just all of a sudden take bivariate Cauchys and then rotate them to get a correlated Cauchy. They need to jump at the same time. This does that. So in these two steps. You really can't do it any faster than these two steps. So if you know how to generate that quickly and you know how to generate that quickly, you can do it. So you could write your own sampler for generating bivariate Cauchys. Or you could go to CRAN and get the multivariate T generator. They have it now. You know, they've had it for probably like 15 years or so. But just keep in mind, you're going to see things where you're like, I don't know how to generate that random variable. You want to be thinking about how you actually do it. Okay, so enough about that. So you want to see something that looks like this. Points in there, and then bang, bang, and bang, and bang. So I'm going to have you play around with these regressions. In this homework, you're not going to fit the big Gibbs sampler to fit Cauchy regressions. What you'll figure out is the thing we've already learned in Stat 101 classes or like that if you have all these outliers all over the place, they teach you to throw them away. I don't like that answer. It really bothers me. This is the sort of stuff that people do to make themselves feel more secure. Like my uncertainties are driven down, so this is the way that it is going to be, and then all of a sudden the stock market crashes and everybody loses their fortunes because they model things using normality or something like that, and they stripped everything away. That used to be the go-to move. And so I don't like that. So I'm thinking about fitting regressions where we have big deviations. I don't know what an outlier is. That word is just, it's more model relative. It's like outlying with respect to the normal assumption. And so there's two different types of outliers to me. There's anomalies that happen because somebody's messed up, or there's really interesting points that did something, and that might be the most interesting part of your analysis. And so, and if you don't think about it and include it into your analysis, you're probably not doing yourself any favors. It feels well good for a while until the stock market crashes or whatever happens, and you're like, shoot, I didn't model that phenomenon. Anyway, we'll be going through a Gibbs sampler implementation of this on the next homework. All I ask you to do is write down pseudocode for the sampler for updating a regression like this. So where we're going with it is you're going to generate data, maybe using this schema, or if you use a built-in package, that's fine with me too. I don't need to look at your code. But later on, we're going to figure out how to infer the regression parameters with large deviations in there. And there's a lot of different ways of doing it. So this falls into the camp of robust statistics. So that means that you've got outliers. And throwing them away is not the right thing. I'm going to change your model. So later on, we'll be inferring all the regression coefficients for everything, and we'll be inferring those as well. So that's where we're going. So I'm going to have you write down that pseudocode for that. Okay, let's look at the rest of the homework. This is a little bit different. This also comes up with a Cauchy distribution. If I end up letting gamma be the gamma 1/2, 1/2, I could turn that into a Cauchy realization. I just want to point out, in a Cauchy regression, these aren't the Cauchy things. So this isn't quite the right solution to the problem, but it's interesting to just work through a bunch of math that's kind of similar so that you can see the differences. I'm going to ask you to work through this problem where you're going to be thinking about this regression model right here. You're going to be generating these y's, generating some regression on things, and then you're going to write down the full conditional distribution. So you'll need full conditionals for beta, for sigma, and for all of the gammas. I want to point out you don't just get one gamma. So the solution to this problem up here is you're just using one gamma. And the solution in terms of the regression context, the way you're supposed to do this problem, is you've got a posterior full conditional for each one of the gammas. I will point out that they're all conditionally independent of each other. And so if you have n data points, you'll have n different full conditionals for those n different gammas. Given you know what the betas are and the sigma and the xi and the yi, only one xi yi pair is informative about the accompanying gamma. So just some heads up. Okay, some easy stuff in here. Prove those things. So this just says trace. So what's the trace operator? Sum of the diag. Anybody else? Sum of the eigenvalues is another way to think about it. So lots of ways to think about traces. I like this sum of the diag because it makes at least this proof. I say to prove this. We'll use that later on when we get into Wishart distributions. We're not quite there yet. But you can almost see the proof right here. You know that the sum of the diag here plus the sum of the diag there, it doesn't matter which order you sum together all those diags. And you can cut through that proof too. We'll use that identity. So on traces. I'll point out that this identity is a little bit more general. It really looks like this. So in a future lecture, I'm going to pull this result out and you'll go, yeah, I remember that. So trace of A, B, C is equal to the trace of CAB is equal to the trace of BCA, and that's it. So you can do the cyclic permutation. So I can bring that one over here. So that's what happened here, and then I can bring this one over here. That's this one. And when I bring that one over here, or the A around on the last time, then it's ABC, and we're back to BA. So all the cyclic things work. If you want to jumble these around, you'll figure out that you can't multiply a lot of these combinations. So they're not conformable with each other. But in general, that's true. So you'll prove that, and we'll use that on this problem that we'll be studying. And I introduced you to a new distribution that's called the Wishart distribution. It's like a multi-dimensional analog of inverse gamma distribution. So I'll just point this out. This is hard to remember at first. But the inverse Wishart is like the gamma, and the inverse gamma is like the Wishart. Okay, why they did that, we will go back and ask somebody later. So it's the opposite one that you think of. But if we're dealing with covariance matrices and we want to put a posterior distribution on those, then we might use the conjugate prior, and the conjugate prior is Wishart on the precision matrix. So the precision matrix is the inverse of the covariance matrix. Personally, I like staring at precision matrices a lot more than I like staring at covariance matrices. Does anybody know why? Does anybody know how you would interpret a 0 inside a precision matrix? I'm going to type up something in a handout for you guys so you can interpret it. It's the partial correlations. I haven't heard that term since I was an undergraduate, so I don't think of it that way. I think of it as entries in the precision matrix nowadays, but they tell us about the conditional independencies. So let me just tell you this. I'll give you a handout that you can read through, so stay tuned for that. But if I ended up having a precision matrix, let's do an example. We looked at this example last time. Xt is equal to alpha plus beta xt minus 1. We'll make sure that this is a stationary process. So this is the auto-regressive thing. I'll say that that's normal 0, 1 error. So this is the auto-regressive model. We will touch this later on. It's kind of fun to play around with time series models. This is a Markov model. And xt is not independent of xt minus 1. In fact, it has everything to do with xt minus 1. It is a Markov. So xt does have something to do with xt minus 2 because xt minus 1 has something to do with xt minus 2. So they're correlated with each other. So, but xt minus 2 is conditionally independent of xt given information about xt minus 1. So provided the information about xt minus 1, I don't need to know what xt minus 2 is to tell you that. So that's conditionally independent. The covariance matrix for this, if we looked at this, however many time steps I have would be the dimensionality here. The dimensionality here, I'd have some covariance here, or I'd have some variance, the original variance of the problem, but then they're going to be correlated with each other. So this is just representing the covariance structure between the xt's, and this would be strong. I'll make it look like this. It's some number, so I'm trying to use shading. And then it would look a little bit weaker here. And it would look a little bit weaker here. And then it would look weaker here. Hopefully you get that. But it starts fading off. And that's representing the correlation between xt and some long ago time point. So it starts becoming more and more independent, but it never loses it entirely. The precision matrix looks totally different. So the covariance matrix for a process like this is dense. So entirely dense, every entry in there is non-zero. The precision matrix will look like this. So it'll be a tridiagonal. And so what it's saying is that this thing right here off the tridiag is a 0. All of these are zeros, which is saying that the thing that is 2 neighbors away is conditionally independent. So that's kind of cool. So for an AR2 process, if I ended up having another lag term, I'd get another band on the diag. So it tells us conditional independent structure. So it's not telling us that that's independent of whatever the original thing was. It's just saying it's conditionally independent. I'm going to give you a 1 or 2 page write-up on that so that you can interpret the precision matrix. Have you guys ever seen that stuff before? It's kind of cool. So it is those regression formulas in disguise. So those conditional forms. So I'll make that connection for you. Just small tidbits that'll help you out. We'll go through this whole problem and I'll tell you what the whole setup is. There's a whole paper on this that I'd like you to look at, and I've posted this as well. So while we're still trying to understand what Wishart distributions are and how to do this Gibbs sampler, you can read through this original paper, and I consider this to be kind of the precursor to the original Gibbs sampler paper. So in 1990, Gelfand and Smith wrote a paper on Gibbs sampling in JASA, and it's one of the most pioneering papers out there. So it tells us all about the math of the Gibbs sampler, why it works, so on and so forth. This paper goes through the problem that they were studying early on. And I'm going to walk us through this problem later on, but it's all about how rats accumulate weight over time. So they've got a couple different treatments. They're going to inoculate a rat with something, and they're going to see how it puts on weight or it takes off weight. So here's their model. I'll give you a full lecture on this model, so don't worry. It looks something like this. It looks like the weight for rat J, I'll call that, let's just use little r. So that's the rat number. So what I'm thinking about is I've got maybe 20 or so rats, cap R rats out there, and I'm going to do something different to them, and I'm going to see how they put on weight. So I'm going to say the rat weight at time t, so that's time. So we've got a double index right here. Their model looks like this. It's going to look like alpha rat R plus beta R times T. It's not an autoregression. So plus some error. So keep in mind, this is 1990. It's a long time ago now. I was in high school. So this is their model. This is maybe normal 0 sigma squared. And so the name of the game is to estimate these rat parameters right here. So these are rat-specific parameters. They belong to the rat. So the idea is, instead of talking about the rat's genetic propensity to put on weight, we think about these artificial parameters out there that shows their tendency to put on weight. So this is an abstraction. So we do this all the time. So this is time. This is your time index right here. So you might have it, encoded 1, 2, 3, 4, 5, something like that for the day number. We want to be consistent on the scale of that day number, if you're going to plug it in right there. But if this is positive right here, it says that that rat has a big propensity to put on weight. Or if this was a negative number for that rat, they would be taking off weight through time. How would you interpret this? Yeah, it's like your baseline. It's your weight when you come into the study. So when t is 0, maybe, if we started encoding it that way, then that would be your weight coming into the study. So let me just ask a question. This is what the whole paper is about. It's their big scientific question. They wrote several of these papers. And so I do want you to kind of skim through it at least, but I'll give you the major gist. We'll come back to this model. But the major question is there a relationship between these two parameters? So they're going to set up this model, and they're going to write this down. They're going to say ARBR is going to be normally distributed. It's going to have some mean. So I'll call this mu alpha, mu beta, if you want. So that's the mean weights. And there's going to be some covariance in here. So this is going to be a 2 by 2. So this is going to have your sigma squared alpha, sigma squared beta, and then I'm going to have this covariance term, and I'll just call it CI-C. It's positive definite, so it's symmetric. It's the same parameter right there. The question is C 0? Or is it something different? Are they related to each other? And that's what the whole paper is about. The part that I think Gelfand and Smith were about is how do you do this inference? Does anybody know what class of models this falls into? So we're thinking about each rat has their own governing parameters. And those parameters themselves are random. So how we're thinking about the universe is we've got a bucket full of rat parameters. Rat 1 comes up and says, give me an alpha and a beta. Bam, and they get them, and that determines how they're going to put on weight through the study. It's not exactly like that. So, but it's some abstraction of the truth. This is called the random effects model. So it kind of feels like alpha and this normal distribution is like a prior, but it's not a prior, it's part of the model. So if I were being a Bayesian, I might write this thing down, and then I might put priors on all those other parameters, on the mu's and on the covariance matrix. And so we're going to need a prior distribution on this thing. We're going to need priors on that. We don't need priors on these parameters because they're already random. How do you handle those in a Bayesian analysis? Just like you would any random parameters. It doesn't matter how you induced randomness, through Bayes' theorem, through a prior, or through a random effect distribution. So I think the big thing is that that's probably not a zero right there. And all you have to ever do is go into a gym. And so go into the gym maybe right around like January 2nd. And you'll see everybody flock to the gym. So it fills up, and you'll notice that there's two types of people in there. So, and the question is how did they walk in? Does that determine how they put on muscle or take off weight or whatever their goals are? I think the answer is, yeah, probably they have something to do with each other. So I'm curious what you guys think. So heavy rat coming into the study, will it put on weight faster or take off weight faster? You could argue this both ways. Yeah, it depends. Yeah, it depends on what they're doing, obviously, to the rats. You know, but maybe if it's big, maybe it has a propensity to put on weight faster. Or maybe there's more to lose, that they can lose it quicker. So it depends on what they're doing. Okay, so that's where this problem comes from. I will be giving you a lecture on Wishart distributions and random effects soon. Let's see what else we got. So you can read through this. It's kind of amusing to read through this paper because if you look at the typesetting alone on this thing, it's pretty nutty. So try to enjoy that. They didn't have, well, they did have tech, right? But Leslie Lamport didn't come in and come up with a law version of it. Does anybody know who came up with tech? I read too many history books. Nobody? Grandfather of algorithms, Don Kennedy. So decided to do that for us. Thank you very much, Don. So helped us out a lot. Now we don't have to do this kind of stuff. But if you read through all of this, you're going to have to be careful. I'm going to ask you to run this analysis. I could give you the data. From here, they do give you the data. It's right here. So I have given you the data. I played a couple different games and threw in an error in the data just to see if you could spot it, because that's how the real world is. So anybody cut and paste something, there is an error in it. Anyway, I'll upload that for you so that you don't have all of the errors in there. But this is the whole data set. This is it. So it's not that fancy. And they have this big, gigantic question of what is that? But you need to go through everything else to figure it out. You need to come up with a joint analysis so that you're controlling for everything. Anyway, read through that. The way that they phrase their priors, they might be using things like inverse gammas or chi-squared distributions, and you're going to need to be able to translate between those two things. So that's part of the exercise as well. That's not happening in this next homework, but it's coming soon. So maybe you get started on that. Probably most important, I also threw on this paper, could Jeffries, Fisher, and Neyman have agreed on testing? And this is where that problem comes from. There's a lot of stuff in here, but this is where I got that problem on the credible sets. So if you want to read about this, you can. I can answer their question in one word, no. Fisher, Jeffries, and Neyman could not agree on testing. They could not agree on anything ever, no matter what the topic is. So, but maybe we could agree. So, Jeffries and Neyman are actually pretty friendly people. So, but I think once we throw Fisher in that conversation, nobody's going to agree on anything. Anyway, lots of good stuff. Bayes factors are in here. So if you just want like kind of a casual read, this is pretty good. So, and there's a lot of good examples in here. I've also posted to the homework this, and this I think you will use for your upcoming homework. here was could Fisher, Jeffries, and Naiman have agreed on testing? Feel free to read on that. I'm not going to test you on anything. And as far as the examples I'm going to pull out of this paper, we've already done it. Still useful. Darren Wilkinson wrote us a nice blog on MCMC and the utility of things like symmetric proposals. And he answers this question not in exactly the case that we're studying, where we've got the precision parameter. They apply everything to an exponential distribution. And just keep in mind the exponential distribution, where the parameter pops up, it's a lot like the precision parameter. So it's positive for one. So if I picked a symmetric proposal and I were able to pick negative values, you would make a mistake. And they talk about this mistake right here, and they talk about how to correct the mistake, and they even illustrate how bad the mistake is. And so I think in terms of my code that I'm going to be showing you, it does have a mistake, and the mistake looks like that. You can't really detect it. You actually have the true distribution and you have samples from the incorrect sampler, they'll look a little bit off. But this is probably a common mistake most people make in MCMC, and we should not be making a mistake. So to make sure that you make the mistake and never make it again, I've made it for you. So, and you can go back and come up with the correct proposal. There's two strategies. Is you could end up using a non-symmetric proposal to deal with this problem. Where to center it is difficult. So that's not a full solution. You could transform the problem as well. So instead of talking about precision, you could talk about log precision and use a symmetric proposal and transform the actual problem. So you do a little bit of math up front, transform everything. You need to take a Jacobian, so because you're dealing with a posterior distribution, transform everything, and then you can work with an easier problem. Okay, I'm going to try to get to some of these details today. We've got 6 minutes. So lots of stuff to read. Let's come back to our problem. We're not going to get too far today. But let's just remember what we were doing. So this is our problem from last time. We had some mu and sigma squared. Just put this up for a second. Our problem is this. Xi's come from a normal distribution. I'm going to collect n data points out of this. And I'm going to try to infer what mu and phi are. So when I want to do it jointly, I don't want to do it marginally. So what I've described is a Gibbs sampler of this format in my code. Now I do want to point out you can actually do this step perfectly, and you can do that step perfectly. But I'm going to presume I don't know what distribution that follows. I'm going to presume I don't know what distribution that follows. I've not done the math. I don't know anything about this. And all I can sample from is normals. So that might bother you a lot because this is a normal distribution right there. So if I do know how to sample from some normal distribution, of course I know how to sample from that. But it won't help you in this later. So this example is done for purely in-class reasons, so that you can understand what all the issues are in MCMC. So this is what my code's going to do. I guess we'll come back next time and look at the code. It's going to run through these 2 steps, but it's going to vary in a Metropolis Hastings step. We'll pick up with the implementation next time, but let's just say I didn't know how to sample from this right here. And you can blend these 2 things together. So this is a Gibbs step right here. This is updating the parameters in sequence. If we were blocking the parameters, so block updating, I don't actually know how to sample from this in general. We know what this thing looks like. It's that triangular distribution. But updating the parameters together is called block updating them. And so that probably is going to make a very efficient sampler, and I've asked you to implement that on the homework as well. So that's the last problem on the homework. So I didn't walk you through that, but you can get started on that. And I've also asked you to update it this way. There's good reasons for teasing these things apart in general, but in this example, there isn't great reason other to explain what the differences are. So block updating says that there's one Metropolis step. You're going to propose both of those parameters simultaneously, and then you're going to go through the Metropolis decision rule to do your updating of those 2 parameters, and you're going to do it all at once. This is a Gibbs step right here,
And this updates the parameters one at a time through the full conditionals. Later on, we'll see some semblance of a proof that says that this stuff works. Right now, we're just going to implement it and see that it works pretty good. Let me just answer a question that you're going to have. Why would you do this over just updating everything as a block? So the truth is you'd probably update those two things as a block if you were going to do it. But a lot of times people do that just out of convenience. But the real reason is, let's say you have like 1,000 parameters that you're going to try to update all together, and they all had some funky relationship. You don't know what that relationship looks like. If you knew what it looked like, you could build a proposal to sample things with kind of that relationship. But the problem's hard enough that you don't know how to do that. And so if I did propose 1,000 things and 999 of them all look good, but one of them was outside the posterior range, I proposed it to somewhere bad, you would reject the whole block all at once. And so what you really want to do is you want to figure out where parameters are very related to each other and update those together. And so, and it will give you more efficiency out of your samplers. And so, I'll say more about that later. So, but there's good reason to do both things. If you have a bunch of independent parameters, then you could probably build an independent proposal and propose some decent locations for all of those parameters to move to. If you have parameters that were highly correlated, you'd probably want to update them as a block and learn what that correlation structure looks like. Again, more details later. So the Metropolis Hastings step for, let's say, number 2, it would look something like this. I'd write down this posterior distribution, and I would notice that all I need to know is in that part of the posterior. I don't need to normalize everything. So my Metropolis Hastings step would be, I would get phi from some proposal. Wilkinson has a long dialogue on what you might want to pick for that. So we'll talk about it later. Talk about it next time. I'll tell you what I picked and why it's not quite right. That's Wilkinson's whole dialogue with you. So I'm going to propose, and then I'm going to build my Metropolis ratio. So I'm going to take the minimum between 1 and this function right here. All I need is the likelihoods. Likelihood given x and mu t minus 1. So keep in mind I have to plug in the old, that's t minus 1. This is conditional on t minus 1. So I have to plug in that layer from step 1. I multiply this by pi theta star, pi phi star. That's my prior. It's just 1 over 4. I do something similar down here. Given x, this is going to be conditional on the mu t minus 1 as well. Pi phi t minus 1. And then I'm going to have my inverse ratio of proposals. So g phi star, and this will be g phi t minus 1 up there. So, and then I decide whether or not I'm going to move to my proposed location or I'm going to stay in the same place. So this is either phi star or phi t minus 1. This happens with probability alpha, and this happens with probability 1 minus alpha. So what I'm going to do is I'm going to have 2 of those steps right here. Key point, this is totally superfluous. You probably wouldn't want to run a weird proposal on this that's normally distributed, because that is a normal distribution and you could sample right out of it. So, but I'll be explaining to you the behavior of Gibbs sampling through this example. Okay, so we're going to have 2 Metropolis steps right here. And that's what the whole code does. Yeah?
On the Metropolis inception, the mu indices be t since you're doing these seconds.
You're right. So in this way that I've done it, this would be a mu t. So that would all be the last previous updated thing. So those would all be t. Yes. Definitely. So we'll come back next time. We'll look at this implementation. I'll show you what happens if you code it up poorly, what to look for. I'll show you what happens when you code it up correctly and what to look for and how to diagnose all this stuff and make sure that it's actually working. So we'll get through that. Then we'll move to the Wishart example, the rat paper. And then after that, we'll go into Jeffrey's brothers. Thanks, guys.